From Canada's Perimeter Institute for Theoretical Physics, welcome to Perimeter Explorations. Classroom videos that investigate the frontiers of science. Join host and physicist Damien Pope of Perimeter's outreach team and leading researchers as they take you on an educational journey of wonder and discovery. The following in-class presentation is available to educators on DVD and comes complete with specially crafted teacher notes. Use of this full package is recommended in order to maximize understanding. Please visit perimeterinstitute.ca for details and to sign up for updates on other products and initiatives that explore the wonders of our universe.
In observatories across the world, physicists young and old are mesmerized by the size and complexity of the universe. Before 1967, physicists thought they had a pretty good idea about what the universe was made of. But that year, physicist Vera Rubin looked at the stars in the outer regions of the Andromeda Galaxy and observed something she didn't expect. The billions of stars in Andromeda orbit the centre of their galaxy, much like planets orbit the Sun. This was no surprise to Rubin. She also knew that planets in our solar system orbited more slowly the farther they were from the Sun. So she expected the speeds of stars in Andromeda to decrease in a similar way, the farther the stars were from the centre of the galaxy. But that's not what she saw. The speeds of the stars remained constant, no matter how far out in the galaxy she looked. What Rubin saw wasn't just slightly different from what she expected, it was dramatically different. The speeds were far higher than anticipated. Why were the stars in Andromeda moving so fast? Was the same thing occurring in other galaxies? Little did Rubin know that her observations would trigger a rethinking of what the entire universe is made of. It's easy to measure the mass of everyday items. A juice carton, a loaf of bread, an apple. But how do you measure the mass of something much, much larger? Like the Sun. To determine the Sun's mass, let's use an approach we'll call the orbital method. We can calculate the mass of the Sun by measuring the orbital speed and radius of one of the planets, such as Jupiter. Jupiter orbits the Sun at 13 kilometers per second. The shape of Jupiter's orbit is essentially circular, with a radius of 780 million kilometers. So how can we use these two numbers to calculate the Sun's mass? Let's start with Newton's second law of motion, which says that the net force acting on Jupiter is equal to its mass times its acceleration. The net force is the gravitational force the Sun exerts on Jupiter. The magnitude of this force is equal to the universal gravitational constant times the mass of Jupiter times the mass of the Sun divided by the square of the radius of Jupiter's orbit. Because Jupiter moves around the Sun in uniform circular motion, we know that its acceleration is directed toward the Sun and is equal to its speed squared divided by the radius. So if we substitute the gravitational force and Jupiter's acceleration into Newton's second law, we get the following formula. If we want to know the mass of the Sun, we rearrange the formula. This formula shows there's a relationship between mass and orbital speed. When we substitute in the speed and radius of Jupiter's orbit, we can complete our calculation of the Sun's mass. So what does this number really mean? Only that the Sun is 1,000 times the mass of Jupiter and 300,000 times the mass of Earth. Now that we know how to calculate the mass of the Sun, let's see if we can calculate the masses of entire galaxies. A galaxy is a vast collection of stars, typically around 100 billion. In many galaxies, gravity makes stars orbit the centre of their galaxy, just like Jupiter orbits the Sun. Because of this, we can use the orbital method to find the mass of a galaxy within the radius of the orbit of any star we choose. To do this, we need to know the speed of the star and the radius of its orbit. Ever hear of the Doppler effect? It's what happens when an ambulance rushes past you and the sound you hear changes frequency. As it approaches you, the sound shifts to a higher frequency. As it moves away, it shifts to a lower frequency. When you measure the shift in frequency, you can determine the speed of the ambulance. It's the same with light. If a star is moving towards us, the light shifts to higher frequencies, closer to the blue end of the spectrum. If the star is moving away, the light shifts to lower frequencies, closer to the red end. Since galaxies are really far away, we can't simply measure the speeds of stars by calculating distance over time. So the Doppler effect can be used to indirectly determine their speeds. The greater the shift in frequency, the faster the speed. Let's use the Doppler effect to help measure the mass of a nearby galaxy called Triangulum, which, like Andromeda, has stars orbiting at speeds higher than expected. Let's pick a star in the outer regions that's orbiting the centre of the galaxy with a radius of 400 million billion kilometres. It turns out that the star in the outer regions of Triangulum is orbiting at 123 kilometres per second. Let's substitute those values for speed and radius into the galaxy mass formula. This huge number is equal to the mass of 46 billion suns.